All right, today I wanted to talk about two things. One of them was table operations. This is how you get the data most of the time now. So what can you do with tables? We have done already quite a number of table operations. We have read it in with NumPy gen from text, but this is the most basic file I/O. So I thought I'd give you a taste of what most people use to ingest larger table sizes, so pandas. But I also use, and Divya as well, uses tables in AstroPy. This is almost the same thing. It's a good example of how you use different packages almost the same way. Sorry, this is the... All right, so we did MCMC fitting, so we actually went a little bit beyond the chi-squared and on the introduced you to the posterior distribution function. Today I want to talk about tables and data frames. So AstroPy tables and pandas. The table/data frame are the same thing, really, close enough. So why are there different packages doing the same thing is a good answer. And so how you join those two. So this is what I just said. Table or data frame is essentially the same thing. It is it's a table. It has numbers in it or other values. Data has comments or text or observer or other things. But if you are a physicist or an astrophysicist, the fact that table has the option to have the unit in there is a huge difference with pandas data frame. The data frame is the nomenclature of pandas, the data science library of Python. So there is a good reason to learn some or a little bit of pandas. AstroPy tables uses the word tables. And that is a very specific to astronomy kind of tables environment, data frame environment. Both AstroPy tables and pandas have a quick functions to read in most types of files that you need to use. So tables expects units, so the AstroPy version of things expects astronomical units. It's set up to find degrees and megaparsecs and solar masses and all this other weird stuff that astrophysicists use. Both work very well with headers, and those are the first rows of a comma-separated values. But there are other kinds of tables that you can read. In fact, I came across a different kind of way to do a CSV file. So it's actually a CSV file, but it gets read in by row instead of like in its entirety. It's new formats keep being added, and then typically pandas has a way to deal with it. Except astronomy has that weird FITS format, which is incredibly niche, never gets used outside of it, and so we need a separate package to deal with that. So for example, if I do this in table, I have loaded in from AstroPy import table, and table read mydata.csv. Table alone in cell will show the table nicely laid out and scrollable. Table show in browser does something very similar, but actually in a separate window. Print table just gives an unscrollable text and names, not type information. This is not the way to do it, right? So you can literally just set in the name in a separate cell in a Jupyter notebook. Just say the name of the table and hit Shift-Enter, and it will show up as a scrollable, very easy to see. .info, that's something that it has in common with pandas, gives out the information on each of the column's properties, the name, the type. Pandas also says, like, this is how many values you have in this column. And then you can notice, for example, that not every column has the same amount of data. Oh, there's some data missing. Oh, I should better deal with that, right? So this is the kind of thing that you get, like, here's all the different kind of table names, and then you also get things like this is a 23-byte long string, which is just weird. I will just be the first to admit that. String. Oh, but this is a float. That's a float. That's a string. So it sort of either has guesses or it already has definitions of how big the string is or what kind of information is in each column. So you can read FITS tables, and that for me is like a major pro, right? FITS is a file image transfer system, which it's not even always an image. Sometimes it's a table, sometimes it's a spectrum, sometimes it's a collection of spectrum known as a data cube. So it has like two dimensions that are spatial on the sky and one that is frequency. So fits are incredibly useful if you're an astronomer, and incredibly useless if you're not. So it's one of those, I thought this is a good example of like, oh, look, niche application. If you are coming in as a general data scientist, for example, and you're coming into a surveyor's office, or you come into something that does stream restoration. I have friends in stream restoration, so I'm just going to grab these people as a random example. They go in, survey what people have done to a waterway, and then go, hey, you could do this. This includes maps, models, and new maps, right? So lots of geoengineering, lots of geospatial information, which is basically GPS coordinates and a value. So it's essentially two GPS coordinates putting you on a particular space and a thing that you want to do. I don't know, height of water table, that kind of thing. Geospatial is really fun. The geography department has this kind of information and deals with that and teaches you Python how to deal with that. But it is the kind of thing where it's like you need GeoPandas. GeoPandas essentially uses pandas to do the same thing. And so that's incredibly niche, except that loads of people use maps. So it does transfer a little bit. But I want to give you this as an example of, look, if you need to read FITS files, this is what you need to do. If you don't need to read FITS files, you can just merrily skip on your way. This is very true for a lot of pandas packages. All right. For example, you can stack table. Vertical stack is essentially concatenating, which is a term that I'm using on purpose because if you've ever used anything like a command line, concat is a command line thing where it's like I have file A and I'm just literally gluing file B at the bottom. So table A and table B better have the same columns because otherwise I'm ending up with Frankentable. Horizontal stack is essentially, so I now have the same rows and they're in the same order and I'm concatenating them horizontally, right? So only if vertically if the rows are the same and horizontally if vertically if the columns are the same and horizontally if the rows are the same, otherwise you end up with Frankentable because it never matches anything. Join is the thing where it goes, okay, I have information on identity for every row. You go, so VStack, Lego blocks, yep, concatenate at the bottom, different researchers' contributions. So essentially, if I send all of you out to go get the same 3 rows of information from everybody you meet, I have you, fill out this little, I don't know, Excel sheet. You and your Excel sheet go out into the world and you come back and I now have 3 Excel sheets with the same rows but with different column entries. I can stack you like that, no problem. I can stack them in any order, doesn't matter. I know that the rows are the same. The HStack, they have the same rows, so this is when you all go out with your Excel sheet and follow each other around and ask every student, you ask question 1, you ask question 2, you ask question 3. And then you go mug another student. So then you become these, everybody has a row to contribute, but they all happen in the same order. The rows can correspond to the same student, or it doesn't matter, which is going to be incredibly rare, right? Okay, so nothing is matched up. This is sort of the raw table glued together. What we usually end up with in data science is that we have table A and table B, and they've been completely they've been compiled by different people at different times with different aims, except there's an identifier in there that I can match you up. For example, all of you have a student ID. What do you think we use that student ID for? To track you through your progress. But not only that, if I have some new information, like for example, what kind of interest rate you're paying on your student loans, right? I have this from a bank, like but they have that student ID in there. I can match you up. I can see how well you're doing, right? If I have, very big if I have the rights to your data. So If you hear me say something like that, do not be alarmed that I can just go happily in my computer and start matching your student IDs with something else up. Like, you need to have data rights to things. This is where privacy comes into play. So if I want to do a research project like that, I have to get an IRB approval. Little sidebar, no, your data isn't freely available to every professor. How horrid would that be? But that means that if you are interested in learning how you do, for example, if I teach a 100 level class, I'm doing okay, I've got all kinds of data on that, but I want to know, hey, I'm missing a few people. Is that the same demographics every time, for example? This is hard to figure out from one class, but you could do this, for example, with 4 or 5 classes if you taught a bunch of them. So then I go to student registration, go like, look, this is my IRB. Can I have the student numbers and, for example, relevant student demographics, like were they freshmen, were they juniors, were they bachelor, that kind of thing. Yeah? So if I have something, there has to be a column that is the same in both tables. For AstroPy, this is sort of the clunkier version. They have to have the same type and name, so you end up renaming a column that actually turns out to be the same one because it was built by somebody else. And so, for example, I have a Heron final.csv, so you can already tell that somebody's been working on this because it's final version number 2. Anyway, and then 2-mass environmental, and then I'm actually casting that as ID, and then I can match the two up. How do I match tables? So, table matching. If I have everything that is a beaver playing a guitar, and or looks like a beaver, sorry, has a beaver tail and plays guitar. This is everything that has a beaver tail and plays guitar. This is everything that has a duck bill and a keyboard. And so in the overlap, if this Venn diagram, of course, is sitting that monstrosity of an instrument with that monstrosity of an animal, right? So they overlap with the same values. Yeah? Okay, so I can join tables if they match up with a particular characteristic or they match up with an identifier. So social security number, patient number, student number. Hey, have a seat. It's about... all right, so you can have different kinds of joins of 2 tables. So a join between 2 tables, you can have the left table and the right table, and an inner join means all the elements that happen in both tables. So only those, right? Only the ones that have entries in both. So I suppose I have a list of patients that had a cholesterol check and a list of patients that had an ER admittance, right? This is not going to be a one-to-one thing. These are the ones. These are the people that have both things happen to them. Yeah. So the inner choice, like and. This is you're in table A and you're in table B. And. You have to be in both. If I do an outer join, that means if you're either in left table or in the right table, which means that you're left with a lot of gaps. Basically, there is no, if I have then my final table, there's like some entries on the left and then none in the right. So you end up with columns that have lots of gaps in them. Are we on? Yes? Okay. Left join, you go, I just want the left table. The left table is my target audience. So even if you don't have an entry in the right table, just leave that blank. But the right one, you can't drop those. Because here you're dropping some of those values in the left table. But if you go like my left table is my target audience, so whatever you have in the right table, match that up. Here's the other way around. So there are 4 ways to join 2 tables. So you can do inner, outer, left, or right. So you have to decide which table is your target data set. Of course, you have to put it in seasonal terms. So you've got trick or treat. So this is an outer. Trick and treat, that is an inner. Trick XOR, so not or. And so that's either, you end up with all the non-matches in both tables. This is phenomenally useless. Trick nor treat, that's nothing in there, so everything on the outside. And trick not and so you end up with nothing in there. and trick and in here or in the outside. Basically, you end up using one of these or left or right. Okay, pandas. This is not the pandas logo. This is the pandas logo. So we can all do this in pandas. And in fact, you'll probably end up doing this in pandas unless you go into astronomy. The reason that I gave you that example for tables was like this is the, so a particular field has made a niche application essentially for, to do the same thing, but so that they can read in tables in their very weird and narrow defined file system. So you can do, for example, like analyze the Titanic passenger data, right? This is one of those data sets that is very, a lot of data science people love, like they have some of these like set piece CSVs. And one of them is like titanic.csv. And so PD is pandas. I've imported pandas as PD, and then read CSV, and then like that's sitting now in a data frame. Definitely never do this kind of big data stuff in Excel because it does things like, oh, is this a date? Like, no, it's not. Please stop pretending it's a date, right? It starts casting things, or it goes, oh, the first one was not a float, so everything, I'm just going to throw everything away after a certain number. Okay, so inspection. So you can just go to the name of the data frame, or you use panda.head, and that actually gives me the kind of information. So this gives me like the top 8, and like passenger ID, that's a number. Survived, yes or no, that's a Boolean. P class is what class were they in? Were they in third class, first class? And then you have a name. And so names are not necessarily part of your data that you need to use. You've got numbers here, but names are there, right? You can actually come out with that. For example, you can do that .info trick that I showed you with, like, again, tables and pandas have a lot in common, but they're not exactly the same. So a lot of the same tricks work, but sometimes you have to go from a table to a pandas data frame in order to do a particular trick. So you have things like passenger ID, survived, what class they're in, name, sex, age. I don't know what this is. Perch ticket, what their ticket was, what their fare was, what cabin they were in, whether or not they embarked. So I think the embarked definitely has something to do with survived, for example. Okay, so this is the 891 entries from 0 to 890. So we have about 900 data points. So you can do the same thing stacking in pandas. So I put the pandas up here. If I go from pandas to, I did first tables because like I'm the most familiar with tables, but I now start doing pandas for certain things because actually it is not important for me to remember what the unit was, for example. So you have a join, you have an inner and outer, and left and a right. But the neat part for pandas is that you can say the left table, the name is ID, and on the right table, the name for the same column that I want you to match up is blob. So it doesn't matter. You can actually give them 2 separate names. But concat is axis 0, that's the vertical, same column, same name, same types, concatenate at the bottom. Absolutely the way that you can do this. Concat axis 1, same rows, same number of rows pertaining to the same thing, not matched up, so you basically stack them that way. So you can do exactly the same thing with pandas. A lot of different packages have essentially the same functionality. But why did people redo it? Because it was specific for their file system, specific for their needs. So you can do merge, which is the same as join, and you can say, well, this is my left table, that's my right table. How? Inner, outer, left or right. And then you could say on what? Left on or right on. So on this names column, this name column, and then you actually can match everything up. You get a new data frame with everything in it. So for example, you can have a patient list with a patient ID, patient list with patient ID, your 2 hospitals, you're merging your, I don't know, cardiac patients. And so now you go like, but they have the same patient ID number because we use the same system for ages. Now I just need to have those 2 merged. So you can merge it like that in no time at all. So you can imagine that this is a very powerful data science tool. A lot of data science is effectively this. Clean up the data, match the 2 things up, and then you have a new data set that has both pieces of information in it. A lot of my science projects with students is exactly this, as you can attest, right? So that's exactly what we do. So why both pandas? Different strengths. Pandas is more flexible on the data frames. It has way more built-in tools. So this is a useful thing to sort of be aware of. AstroPy can read an astronomically specific data templates and remember the units. And honestly, there's some tricks with units, so you can convert from one unit to the next just using the function convert. Well, if you've ever done a unit conversion from CSI to Jansky's or the other way around, you go like, what? Which way does it go? Now you don't even have to remember it. You can just have that do it for you. So why not both? Well, you can make a data frame by going table to pandas, and table is table from pandas, so you can actually use data frames. You can read in a data frame and turn it into a table. I highly recommend it to not do this more than once, because then you have, now you have a table, you do table things, and then you're like, oh, I'll switch back to pandas. These conversions don't work great all the time, and at some point, where you are in your Jupyter notebook, you don't remember, wait, was this now a table or was it a data frame? So it's best to sort of go, all right, at the beginning, I don't need units, I'm going to use pandas. I do need units, I'm an astronomer, I have these FITS files, I'm going to use tables, and that's what I'm going to stick with. But you can switch back and forth. And I know I use stone old memes, but I'm old and I'm good with that. Yeah? So see how who here had heard of pandas before? No? Who had heard of the term data science before? Who here would like a data scientist salary? Right? It's a good one. So the reason for this is that a lot of the time, various companies or scientific collaborations, for example, have produced columns and tables for a particular thing. And then you go, well, now I have multiple tables, and they all sort of pertain to the same subjects, targets, science experiments. Now I want to combine them. Combining different pieces of information over multiple experiments is sort of what you do here. And then from the aggregate, you can get new information. And that honestly is a lot what data science is. So useful tool to have, pandas. So you can do a sanity check. For example, with pandas, you can say isNull is very similar to the NumPy utilities. It returns an array of the true false. So isNull sum returns the total number of null values in the data frame. It literally sums it in both directions and go, how many missing data do I have? How many NaN values are sitting in there? And so is this big data? No, but this is sort of like the very first step. Cleaning up data, checking out for gaps in it, matching them up, or just concatenating all the little files that you have from like a whole survey team. That is sort of the job of a data scientist, making a nice clean data set. And then, when we're done with that, we make plots, what we've been doing for ages now. Yeah? Okay, so pandas is a useful thing to learn. I'm just pointing that out to you here. Like there is a ton of information. Like it's much more general than just physics. So that's the kind of thing you're going to go like, I would like to have a little extra in my back pocket when I graduate. Hey, doing a Udemy or something course like that on pandas, which is very generic, is a very useful thing to do. It's sort of if you change over to data science. Here's the fun part. You could work in tables for a whole research project, do the whole thing, and then realize, oh, those things are equivalent in pandas. Well, then you've done the science part, and then you go, I also know how to do the data wrangling part, and I know how to do visuals and statistical tests, and all. That's the stuff that we're learning here. Okay, so it's not really the big data part, because tables, what's a big data table? All right, now it's the second part of the class, or the last 15 minutes, which I really want to have a little bit of discussion, because hey, it's the elections tomorrow, and it's always a very favorite of mine to go look at election visuals and go, So I am not one of the people that I cannot vote here, so I feel like, there you go. I live here, I can vote. I find the elections map very useful exercise in rooting out biases, including my own. So what does a map highlight and what does it hide? So if you see an election map, if you see this anywhere really, how do the bias of the maker and the viewer sort of play in this whole thing? Usually, this is the first one to look for. Is this secretly a population density map? For example, if I look total number of votes for candidate X, I'm usually just looking at the red dots here, right? There's more people per square mile. There's more than 5,000 people per square mile here in the Louisville area. So yeah, if I'm looking at number of voters without any other normalization, I'm looking at this map, no matter what I do. Okay, so media coverage is always a fun one. If you, yes?
Do you know if we have tomorrow off?
No. Louisville, U of L doesn't because we're not a voting station. All the high schools and middle schools and elementary schools do have off because they need the gym for voting. So, all right. I got a chuckle out of this one. No new business development is too small. On Monday morning, a stop in Richmond, Bashir cited a recent opening of a rest stop just outside town. We even bought a Buc-ee's to Madison County, he said, referring to the franchise's first outpost in the state and a point of local pride. This is phenomenal for like, wow, does the New York Times get out much? Because if you've been to the Buc-ee's, there you go, like this is as large as some of the villages I've been to in Italy, right? It's enormous. It is a lot of jobs. That's a thing to point out to. I know there were Courier Journal articles. Oh my gosh, the first Buc-ee's is coming to the state, right? This is a big deal. So it's kind of funny to watch the outside press to get that one a little wrong. So it's always good to go like, okay, where does it come from? What kind of bias does that particular outlet have? And so as soon as I Google this, one of my first hits is from 2016, which is not this election. It's not even the right election. So, so always pick out, like, you couldn't actually tell. I had to dig that out of the article that went with it. What's the first thing that you notice about this particular map? Predominantly blue, okay. But what else can you tell me about the color map?
The colors aren't very sporadic, they're more or less grouped together.
Okay, well that would be useful information. You can sort of say like, well, these counties this seems to be matched counties, yeah.
It doesn't tell us either by what margin it's actually the blue or red by, and it also doesn't tell us the population.
Ding. If this is 2 people over here, sorry, there's 3 people over here, and 2 of them voted blue. Now this entire square is blue. And that's a margin of 50%, so woo, huge margin. So if you plot that still doesn't tell you, because I don't know, like this one here is incredibly population dense. Some of them here are not. I, for example, could project a bias on here, right? I could say, well, all these over here are completely empty. Hardly anyone lives there, right? That's not true. There's several cities down there. They're not maybe major. It's not Boston, but there's a city down there. So it's not all rural, inhabited by 3 folks, right? So that's not. So you can project biases on this easily because it doesn't give you any nuance. Like it goes one color or the next. Of course, media love this kind of thing because it's a nice, easy narrative, right? I can say the entire country of Jefferson turned blue, like as if no Republicans live here, right? So it discounts people very easily. All right, the 2019 map. Okay, here's the 2019 map. What's my first problem with this?
Well, once again, it's not really, it doesn't tell you any actual data. It just has like scaling, gradient, colors that aren't clarified.
Where's my scale, right? I haven't labeled anything. I'm trying to not swear here, but it's like this is the kind of thing where I get really sweary about. Because I'm going, you have not told me what this bright red color is versus this light red color. Is that the number of voters? Is that the margin? I'm guessing it's the margin, but it wasn't explained, right? Okay, better. Okay, yes, thank you, Courier Journal. 2019 election. Governor's race tells me what's what, tells me the names, which is good. tells me the margin by county. Now it tells me the actual what's happening. And the interesting thing is that the margins actually aren't that strong everywhere, right? It's like, oh, it's way more nuanced than my bright red, bright blue map. The other thing is, the thing that it doesn't show is how populous this is, right? Is this a very populous county or not? Unless you have intimate knowledge of the state, or you go back to here, you kind of go, looks kind of green. So maybe that is not terribly populous, but if I like, well, here's Louisville, Owensboro, Bowling Green, and Lexington, and Covington. It's like, yeah, those are cities.
A 35% margin in Louisville is probably more that's probably more Democratic voters than the entirety of that red area down at the bottom.
Correct, right? So a margin like this, if you are actually tallying up all the votes, how much does that tell you? That's another thing, right? What kind of vote was this? Was this by precinct? The person who wins the most precincts wins the state, or is it the person who wins the most vote total wins the state? So that also tells you where you should, I don't know, run around in the state itself, right? If you want to get enough votes, you can sort of go between these 5 points and rack up enough votes to get there. And if it's like, if you want to do precincts, you're going to have to visit all of them. But that also is the kind of thing that comes out of a map like that. Oh, look, this is a map that actually tells me sort of what's going on except for the total number of votes. All right, I can also do this. So each circle size is proportional to the amount of each precinct's leading candidate is ahead. So it's not the total number. My favorite one that I've seen was from, I think, XKCD, where they put a little person on every state how many voters there were. So it was matched like that. Because again, you get a big margin here, but it's still unclear how many people that is. So I think that's actually by people. Still in 2019, because I couldn't find any, Kentucky always has hardly any polling. Because it's a small state that you then have to, with not a lot of people, and then you have to truck around a fairly large distance in order to get enough of 1,000 votes, or you get everybody to answer the phone, which is also a biased way of measuring things. So you can kind of go like, okay, we still get margin, and we get change in margin. So this is actually sort of a second derivative. So I can actually see trends, for example. I don't envy the media here, because now you have to extrapolate from light data. 2019 is a while ago. It's 4 years ago. We had a whole pandemic, a tornado tore through the state, the other half of the state flooded. Stuff happened, right? We're not the same people as we were 4 years ago. So extrapolating from sparse data and not having recent data is not helpful. So does everybody show up and just simply vote by party line, right? So this is the party affiliation lead. So like you have about equal numbers, and like this is where you have are heavily Republican and more blue. But do you extrapolate from this?
It's also a margin of 3,000.
So it's yeah, that's not a great way. That's not a good way to extrapolate. Maybe it's a critical policy, right? So Amendment 2 is one that is not a terribly popular amendment to, but you can see that the voting has changed, or like what the ratios between that is. How much movement in the past? So how much shift over the last 4 years? Like this is the last data we have. All our data is old. 4 years is a huge amount of time. In politics, it's a huge amount of time just about anywhere, right? Big shifts happen in 4 years. So, or you get something like this. No, that's the population growth. That has nothing to do with it. But I clicked on it because it was in red and blue. And red and blue are now ingrained in our brains as. So you have things like, oh, actually this is the area, like these are 2 areas of Kentucky that are emptying out, and basically everybody's moving to the middle. So, discussion-wise, like these are all the maps that I could find. If you can find me another one, or we'll see how it actually ends up. But notice how some maps play into biases, right? So if you have margins, but then you tend to discount things because like, well, that has a really bright margin, but I'm sure nobody lives there. Well, unless you go check, that's a bias. Like you're projecting a bias on the map. Not even the person who made it, you are helping your own bias by just discounting something. Another thing is that, well, you have to make a choice. If you have a simple narrative, if you have a 30-second segment to go say, look, Kentucky turned red because, you know, most of the precincts turned red. If that's your narrative, then you only need the first map. Any other map is adding way too much nuance to the whole thing. If you go, I have a 20-minute segment on this, I can go talk about it a little bit in detail. So I'll have a couple of maps, one of them with the margins, one of them with like the Amendment 2 or another kind of major policy shift, or like how popular another politician was. Like, you can then put that in context. But I think you should always start with this one. Where do people live? And this also sort of puts priorities for people. I'm sure that people in the green areas care very much about agricultural policy, for example. And the people over here, probably a lot less. You don't have to. It's far away, right? So there are different demographics to take into account. It's always going to be a knotty problem, and the kind of narrative that you want to say means that you're going to drop a few things out of your map. By definition, you sort of have to. Okay, anyway, so I'm very curious what the maps are going to be looking like, just what people are going to show, what does the Courier Journal show, what does the 538 or whatever, it's now CBS News, I think. But so yeah, you can data nerd out here, and it's quite fun to do. All of this stuff is made by GeoPandas, or you can make them really quickly. You get the boundaries are essentially GIS data, so you can load that in, and then you can basically project a table onto these kind of things. You can say, I want this by county line, I want this by larger districts. Like, all these things are available from the Survey Bureau. Any comments? I hope everybody's very clear on the fact that I do not want to project any kind of voting advice here. I just want you to look at the actual maps with some critical thinking, like, what exactly did they leave out? What exactly are they emphasizing here? This is true for any media, because like, they want to go with a easy sellable narrative. So they always have to make that choice anyway. So, any comments? Did I do a good job of, you know, you can tell which way I would have voted in 2019?
Well,
You know,
I can guess.
we can all guess, but I didn't like, I couldn't.
I don't think the presentation itself gave that.
Okay, good. Yeah. No, that's important to me, right? So, and it's also important to me to kind of, like, for example, I remember 2019 we talked about this, and like the fact that this was all red, and it's very easy to discount that as not, or all rural and not urban, for example. Meanwhile, you go, not urban. What are those red dots here? Those are mid-sized cities, right? So it's easy to project your own biases that way, and I find that very useful to think about. So I think about these maps like, okay, what did they show? What did they not show? So median income, for example, is completely missing out of this whole thing, which could be a consideration, right?
Yeah, I feel like the bigger issue is that you're a physics professor giving this, and, you know, I feel like you can make a pretty reasonable assumption on which way you would vote in 2019 based on.
You'd think, right? But a lot of physicists are enthusiastic about the military-industrial complex because lots of money. So
More just professor is the bigger thing in that. Yeah, what happened in 2019 where 90% of teachers voted for.
we're not a teacher, though. We're not in that particular thing. It could be like
Related.
related. Okay, that's true. All right.